Hi guys. So in the last lecture we talked about random variables. Today we're going to start talking about probabilities. So let's start with exactly the same experiment that we conducted last time, that we're going to take a coin and we're going to toss it 3 times. Let's write down all the possible outcomes of the experiment right here. So if we toss a coin 3 times, we could either get a head, head, head. We could get a head, head and a tail. We could get a head, tail, head. We could get a head, tail, tail. We could get a tail, head, head. We could get a tail, head, tail. We could get a tail, tail, head. Or we could get a tail, tail, tail. So we've conducted an experiment, and these are all the possible outcomes of that experiment. So this is basically called a sample space and denoted by capital Omega. Let's further take the experiment and define the probability of a head as P and probability of getting a tail as Q. Now in our experiment of tossing a coin, we can either get a head or a tail. These are the only 2 possible outcomes. So we're further going to define probability of getting a head plus probability of getting a tail as 1. Okay. Now what we need to do is, I would like to actually define what is the probability of all of these outcomes. So in particular, let's start by defining the probability of getting a head on all the 3 coin tosses. Now before we do that, let's understand that these coin tosses are going to be independent from one another. And if they are independent from one another, we could actually write it as probability of a head multiplied by probability of a head multiplied by probability of a head. And according to our model, that would be P times P times P equals P cubed. So we can write the probability of this outcome here as P cubed. Now similarly, with the same logic, the probability of getting 2 heads and a tail would be P square Q. Again, 2 heads and a tail would be P square Q. Of getting 1 head would be P, getting 2 tails would be Q square. Again 2 heads, so P square Q. And here we're going to get 1 head and 2 tails, so PQ square. Here again 1 head and 2 tails, PQ square. And here 3 tails would be Q cube. So these are the probabilities of getting any one of these outcomes. Okay, so we've written the outcome here and what is the probability right here. Now let's just check that if this is a financial this is a model that we've created. Actually, let's just make sure that our model agrees with our intuition. So let's define an event. Okay, let's define an event A equals getting the first coin toss a head. So we want our first coin toss to be a head. That's the event that we define, and we would actually like to find out what is the probability of getting a head on the first coin toss. Okay. So if you look at all our sample space, we could see. Let's figure out what are the events, what are the outcomes actually that result in head on the first coin toss. So we see 8 outcomes here. This is the first coin toss, this is the second one, this is the third one. So as we can see, we get a head in these 4 outcomes, okay, only, and whereas the other 4 outcomes would give us a tail on the first coin toss. So we basically, when we say first coin toss a head, we are interested in finding probabilities of getting either a head 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 or a head head tail or a head tail head or a head tail tail. So this is same as a subset containing the following outcomes: head, tail, head, and head, tail, tail. So this is the subset that we are interested in. We want to find out what are the probability of getting a head on the first coin toss. Now intuitively, we know what is the probability of getting a head on the first coin toss, and that is basically defined right here, and that's equal to P, right? That's exactly how we've defined the probability of a head, which is what is the probability that the coin toss results in a head. So that's exactly what our intuition says this should actually lead to. And let's check mathematically if our intuition agrees with our financial model, and that's exactly what we're doing here. So we've listed out all the possible outcomes here that result in a head, and we already have a probabilities listed for these. So this would simplify to probability of a head, 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 plus probability of a head, head, tail, plus probability of head, tail, head, plus probability of a head, tail, tail. So this is finding the probability of the subset is exactly equal to, you know, probability of getting all of these, you know, sum of all of these outcomes. So we can write that here as PQ plus P square Q from here plus P square Q plus PQ square. Now further solving this, we could take P square out, so we get P plus Q here. We can take P and Q out, we get P plus Q here again. Now if you see from this equation A, this goes 1, this becomes 1, right? So we are left with P square plus PQ, and we can further solve it by taking P out, and we get P plus Q, and this again is 1, so we finally get P. So as you can see, you know, we started with a model where we defined the probability of getting a head as P, probability of getting a tail as Q. We tossed the coin 3 times. These are the probability of getting individual outcomes. Then we defined an event, and that event resulted in a subset containing 4 elements. We wanted to find out what is the probability of this. Intuitively, that probability was the same as P. Then what we did was we basically solved for this probability. We took a sum of all individual probabilities of all individual outcomes, and after solving it, we also got P. So our financial model kind of agrees with our intuition, which is great. Now what we can do is we can actually generalize this. We could say, okay, we are interested in talking about a probability space. Okay, so we want to talk about a probability space. And that to a finite probability space. Now what is a finite probability space? Finite probability space is basically a probability space we get, a probability space we get by conducting an experiment which has finite number of outcomes. So for example, in our coin tossing experiment, we basically had only 8 possible outcomes. So this was basically a finite so a probability space that results from a finite experiment is called a finite probability space. So let's assume that we have a sample space, a finite sample space denoted by omega 1, omega 2, omega 3, da 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 da. So this is basically a generic sample space for us, okay, and we denote an outcome in that sample space as omega 1, omega 2 likewise, okay. Many a time we want to actually talk about a generic element of this sample space, and we actually do not even write the subscripts. We could just write an omega, okay? And omega basically means a generic element of our sample space. So what we want to do is we want to define what a probability space is. A probability space basically needs 2 things. It needs a sample space and it needs a probability measure, okay? Now sample space you already defined, right? It basically is a collection of all possible outcomes of an experiment, okay? So in the previous example, we listed out all possible outcomes of our experiment, and that basically was the sample space. Now we haven't defined what a probability space is. So basically probability space, a probability measure is. So a probability measure is basically a function that maps a generic element of our sample space denoted by omega, and it maps it into a number between 0 and 1. And this is called a probability of that particular outcome. So what is it doing? It basically it's a function that basically takes the outcome and assigns it a value between 0 and 1. Now obviously we need to actually constrain this function a little bit, so we further define the following. We say that if we sum the probabilities of outcomes, okay, of our sample space, and omega ranges the entire sample space. So we're saying that we're taking a sum of probabilities of each and every outcome in our sample space. That should equal to 1, okay? So if in other words, if we sum the probabilities of each individual outcomes, that should be equal to 1. Okay. Now, many a time we would also like to calculate what is the probability of a subset of our sample space. Subsets are, we can define it by A, basically any subset of our sample space. Okay, so we want to find out what is the probability of that subset. So if we look at our previous example, we defined an event of getting a head on the first coin toss, and that event basically resulted in a subset defined by these four elements. Okay. Now, when we wanted to find out the probability of those 4 elements, it was same as summing the probability of each of these individual elements. Likewise here. Okay. So same thing here. Now here again we want to sum the probabilities of these outcomes, but instead of the previous example where our omega belonged to the entire sample space, we were summing the probability across the entire sample space. Here we are only going to sum probabilities of those elements that belong in our subset. Okay, so as simple as that. Here we were summing across our sample space. Here we are summing probabilities of only those elements that belong in our subset. That's another important equation. Now, from here, since omega basically is our sample space basically contains each and every element of our experiment. From here, we can deduce that probability of is very simple, right? I mean, basically, its probability of each element should sum to 1. This basically has each and every element of our experiment, so the probability of getting an outcome in our sample space by definition should be equal to 1. So that's pretty much what I wanted to talk about in probability spaces. So we started with an experiment, and then we just to recap, we basically started with an experiment. We basically defined a financial model here. Then we defined an event of getting a head on the first coin toss, and we made sure that the intuition basically agreed with the model. Then we further went and said, okay, we're going to define a finite probability space, and we said, okay, a finite, if we conduct an experiment that only has finite number of outcomes, that basically is our finite sample space. Okay, and for a probability space, we need a sample space and we need a probability measure. And probability measure is nothing but a function that assigns each and every outcome in our sample space a value between 0 and 1, such that sum of probabilities of all our elements in that sample space equals to 1. And if you want to calculate what is the probability of getting of a subset of our sample space, it's given by this equation. And then we further said that probability of the entire sample space would be equal to 1. So one important thing I would like to actually point out here is, in the last particular lecture when we were talking about random variables, we never really talked about probabilities. So we defined an experiment of tossing a coin, and on that experiment we constructed a few random variables. And as we concluded in the last lecture, that we could construct random variables without really talking about probabilities, right? Now, if you look at this particular example, we've done just the opposite. So here we wanted to talk about probabilities, and we said, okay, we have a finite probability space, and we defined a probability measure on that space. And probability measure, we said, okay, just a function that maps any one of these outcomes into a number between 0 and 1, and that basically is called the probability of that particular outcome. But while we were doing all of this, we never really talked about what the random variable was. So it's important to realize that random variables and probabilities are pretty much two separate concepts. Many a times what's going to happen is, we're going to actually, later down the road, we're going to actually talk about two different measures. We're going to talk about a probability measure in the real world, and we're going to talk about a probability measure in the risk-neutral world. And as we move between the real world and the risk-neutral world, our random variable wouldn't change, okay? A random variable would be exactly what we've defined it to be, only the distribution of the random variable would change. So far, we haven't really talked about distribution, and we're going to do that in the next particular lecture. But still, it's important to realize that random variables and probability measures are two separate concepts. And when we change the probability measure, the random variable doesn't get affected. Okay, the random variable basically stays the same. Only its distribution will change in the two separate measures. So with that, I would actually like to conclude right here. In the next lecture, we're going to talk about probability distributions of a random variable.